Hello everyone, welcome back to my channel Ordinary Data Scientist, where we talk about data science. So friends, in the previous videos we had covered a lot of topics from the third chapter. In this video we will try to cover the remaining topics. So the next topic is how to find these variance and standard deviation in sample. So earlier whatever formula we saw above were mostly in population. We studied the formula using the mu, and you know that mu is represented for population, and for sample we use small s. Now how to find the sample variance and sample standard deviation? So the formula remains same, that you need to find the distance of each data point from the mean, which is x bar now, and then you square and then you divide by n-1. The only change you might have noticed that in population we had sigma square is equal to sum of all x minus mu squared divided by capital N. Now instead of n we have n-1, right? So that's the only difference you will see in the formula of s squared and s. Now if you want to read why n-1, why not n, you can go on Google and you can do more research on that. I'll just try to keep it short based on my understanding from this line which has written in the book, that we want n-1 because we want a good estimator, right? Both sample and variance deviation use n-1 in the denominator, and this is because of good estimator. Okay, so what is good estimator or what is unbiased estimator? We'll talk about that. Okay, so now I just took a screenshot from a video which I have given the link below. Now in this example we have three sample, this sample 1, sample 2, sample 3, taken from a same population. All three are taken from the same population. Okay, now same population. Now population parameter, if you see, which is nothing but population mean, is equal to 5. So if I write population mean is equal to 5. Now we need to identify that which particular sample A, B, C, which particular sample displays the estimator with both low bias and low variability. Okay, so we need to understand that. Cool. Now coming back to this example, if you see the mean is 5, that means the sample that we have should also have mean close to 5. Now here we have 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. Now if you take example of statistic C, the mean will be somewhere here, which is way lesser than our population mean. That means C cannot be a good representative of the population. Okay, now coming back to here, if you see both sample seems to have a mean of 5, right? Here also x bar tends to 5, here also x bar tends to 5. Okay, both are good in terms of low bias. But if you talk about low variability, here if you see the variability is very high, right? The distance from the mean to the end data points is very high, while here the variability is very less. The distance from the mean to last data point is very less. So our answer will be statistic A, where we have low variability and low bias, and it's a good representation of the population also. So that's what you can understand the estimator briefly. But if you want to study it in detail, feel free to watch these videos and some papers where you will find more explanation about this topic. Okay, so now let's try to remember that the sample variance and standard deviation will have same formula with added n-1 instead of n. Okay, so this is sample variance and sample standard deviation. Now people, a very important concept of z-score. It is based of few coming chapters, so please try to understand this. Okay, so z-score. What is z-score? So let me try to say that if you have 140 rupees and if you want to convert into dollars, what do? You divide it by 70, 140 divided by 70, and you will say it's $2. So if you want to convert something to something, you generally divide or multiply it by that, right? Let's say if you have 1000 meters and if you want to convert into kilometers, you will divide by 1000, to convert that into kilometers. Similarly, if you have 1 kilometer and you want to convert into meters, you will multiply by 1000. You will do something that, right? Similarly, Z-score is nothing but in a layman language, if you want to understand, it's a conversion of the distance, of any data point, from mean, mu, in sigma units. Okay, now let's say you have a distance of any point, let's say x1. How will you calculate x1 minus mu? And if you want to convert this into Z-score, you will divide this by sigma times how many times, and this is called your Z-score. Means your Z-score will say that a data point is x sigma times x sigma times away from mean mu. Now if Z-score is negative, that means it's on the left hand side. If it is positive, it's on the right hand side of the mean. So that's how we can understand Z. Now if I take some example, now if you have any data point on the axis, you can calculate the Z-score, right? Z for x1 will be x1 minus mu divided by sigma, whatever sigma it is. Similarly, Z for x2 will be x2 minus mu by sigma, right? You can calculate this Z-score. Now what is the importance of Z-score, we'll see in the hypothesis testing in next chapters. But as of now, let's try to understand what is Z exactly. It's a distance from the mean divided by sigma. Okay, so that is your Z-score. So there are a couple of examples. I'll request that please try to solve those examples. Now there is another term of coefficient of variation, which is nothing but your sigma divided by mu into 100, means you are converting that into percentage. This is also try to give a kind of a sense of variation, and as I read, this is mostly used in financial statistics. So you can remember this formula, that coefficient of variation is equal to sigma divided by mu into 100. Okay, so people, all the analysis that we read till now was on ungrouped data. We had the data points spread across the axis. Now if you want to do the similar kind of analysis like mean, median, mode and all on the group data, like we had one group data, I think in chapter 1, where we had the unemployment rate of Canada, and then we did this frequency table, right? So if you want to find the central point like mean, median, mode of this kind of data, how will you find? So the formulas are there. It's a pretty straightforward. You need to just follow the formula, and you will get the middle point of this kind of data also. I won't go into detail because this has nothing new to add apart from the formulas, which you can probably apply. In the next video, I will also try to show that how this central point in the group data is different from the central point in the ungrouped data. Like let's say in the group data, we are saying that mu is equal to 6.93. Now if I had the ungrouped data for the same set, what will be the mu there? So I'll do this calculation in the next video, okay, on Excel. Now we'll talk about the another important concept of skewness and kurtosis. Okay, so what does it mean? Now here people, if you see, I always say that this is a normal curve because it's symmetric across the central vertical line, it will be symmetric. The left hand side will be equal to right hand side in terms of the distribution, in terms of the shape and everything. But what if you have this kind of lines or this kind of distribution? If you could have had, right, this kind of distribution also, like a lot of data points are kind of concentrated towards your left hand side. Here it's very concentrated towards your right hand side, while it was concentrated towards the middle point only. Now if you have this kind of data points, what exactly it says? So this is nothing but your skewness in the data. We call it skewness in the data. Now this is normal distribution, this is good. And if you see this has a long tail on the left hand side, right? Long tail is the skewness, okay? Now this will be called negative skewed because it has the long tail in the left hand side. So that's why it's called negative skewed, okay? Similarly, if you have this case, a long tail, if you see it, long tail is in right hand side, so this is called positive skewed. Means the most of the data points, there are smaller data points, but most of the data points are towards the right hand side, so this is called positive skewed, okay? So these are the three kind of skewed data that you will see in your data, right? Is like symmetric distribution, which is nothing, normal distribution. This is negative because the left hand side is the skewed, and this is positive, which has the right hand side skewed. Now people, one important thing that we need to understand is that if you talk about the normal distribution and I plot this vertical line, what does it mean? The vertical lines, I say this is mean, mu. What do you think? Where will be the mode and median will be? What do you think? Okay. So if it is mean, if it is the mean, you see the mode is also this point, right? Mode is also this point because the maximum data points are of this data. And we also said that this divide 50% here, 50% here, this particular vertical line. So this is median also. So this data point alone has all the three central tendency. Like this data point is the mean of this curve, mode and median also. Okay. So normal distribution, everything is concentrated to one data point. Now if you have, let's say, the positive skewed, what will be the case? Now in the positive skewed, one thing is very clear, that this will be the mode. The maximum data points appear here, and median, if you see, median will be somewhere here, right? Median, mode, median will be somewhere here. Now mean, if you think people, mean will be the average. Now the right hand side is little skewed, like most of the data points are on the right hand side, which are the bigger data points also. So the mean will go away towards the right hand side. So mode, median, mean, this is the right skewed. Similarly, if I take the example of your left skewed or negative skewed, this will be the mode for sure. Median will be somewhere here, and as the data points are going away from the center location, mean will be somewhere here. Mean will also shift towards the left hand side. So this is the shape of, say, three kind of skewness and how the mean, median, mode will be located in these three kind of graphs. So there is one thing, the coefficient of skewness that you can probably remember, that this is 3 times mu minus median divided by sigma. So using that, you can try to find that how skewed the data point is. So if it is positive, you will say it's a positively skewed. If it is negative, you will say that it's a negatively skewed. Okay. So quickly, kurtosis is like three kind of kurtosis you can see here. It shows the peakness of the curve. If the peak is very high, it's called leptokurtic, and this is the normal curve where the peak is not very high and it's very not very flattish also. Okay, it's a mesokurtic. So just shape of the curve in terms of the peakness. Now let's discuss, I think, one of the last concept, which is box and whisker plot. Sometimes we call it box plot also. Okay, so let me write it here, box and whisker plot. So if you remember, people, we had the Google example where we saw the minimum was around 2 lakh and the maximum was around 56 lakhs, and there was the data point of 25% and 75%, right? Now if you have this data, and if you want to, we call this is interquartile. If you remember, this Q3 minus Q1, we call it interquartile range, right? Quartile range. Now if you want to try to find out that, okay, I know the salary, whatever, let's assume this is 9 lakhs and this is 25 lakhs. If I assume that, okay, 9 lakhs to 25 lakhs is an acceptance range where 50% of the population lies, up to what range I can stretch and I can consider that as a acceptable range. Okay, so this is what we actually try to find using this Box-Whisker plot, like up to what point we can stretch and we can consider those data point. Cool. So the formula for this particular point, let's say this is x2 and this is x1. The formula for x1 and x2 will be, your x1 will be your q1 minus 1.5 times your IQR, interquartile range. Similarly, here x2 will be your q3 plus 1.5 times your IQR, the interquartile range. IQR is nothing but interquartile range. This is your IQR. This is called x1 and x2. Okay, now this x1 and x2 is called inner space. You don't need to remember this term, but generally the box plot will be x1 and x2. You need to find using this formula. Okay, now this is called your inner space, INNER spaces. Both are. Now if some data point is still outside here, like let's say 56 and what, if the data point is still there and you want to see that, okay, I want to increase my range and also want to see that, okay, even after that range, how many data points are there and how many data points are outside that range, you can plot y and y2. Now this space will be called your outer space or outer fences, outer fences or outer space, outer fences. Okay, so yeah, so this outer y1, if I write the formula, y1 is equal to q1 minus 3 times of IQR instead of 1.5, and y2 is equal to q3 plus 3 times of your IQR. Now if you come back here, you will see the formulas like the inner fences and the outer fences. You are increasing the boundary by 3 times of IQR. Okay, now people, if you see this one, this is q1, this is q3. The inner fences was still here, right, till here, inner fences, and then you are increasing outer fences by 3 times of IQR. Okay, IQR. Now in the Google example, if I go, people, I can calculate x2. X2 will be your q3, which is 25 lakhs plus 1.5 times your IQR is 25 lakhs minus 9, which is 16 lakhs. So this will give you 25 plus 24, 49 lakhs. So even it didn't touch the 56 lakhs, so it will be around 46 lakhs here, right? 46 lakhs. So definitely this person is falling beyond your inner fences. So this data points is your outlier. Similarly, you can calculate x1, which is nothing but x1 will be your 9 lakhs minus 1.5 times into 16. That will give you your 24, which is negative. So yeah, 2 lakhs is still falling under the inner fences, but this data point is not falling under inner fences. So this 56 lakhs is your outlier. So that's the purpose of your box and whisker, to find the outlier in the data. So that's the purpose of your box plot. Okay, now generally the box plot you will plot, if you plot using Python or R or any language, it will look like this. So here you have the hinges. Again, you don't need to remember these keywords and all, but just for reference, these are the hinges. This will be your median, this will be your Q1, this will be your Q3. Okay, and this is your inner fences, and this is your inner fences towards the Q3. Yeah, Q3 plus 1.5 times IQR, and this is your Q1 minus 1.5 times IQR. So that's how the box plot will look like in the any programming language. Okay, cool. And we'll solve them using Excel in the next video. I'll request that please go through the formulas here very quickly and try to revise them. So with that, people, I'll stop here. I covered the chapter 3 in almost like 4 videos. Next video we'll have the problem statement, try to solve in Excel, and then we'll move to the another chapter, 4th chapter on the probability, which will be really interesting. But let's try to solve a couple of examples and all the problem statements in Excel. So I'll take a pause here. I'll see you in the next video. Thank you.